So as you are all familiar with this, there's basically two different media through which light is required to travel from point A to point B. Okay, the thicknesses of these two media are specified. So this is D1, D2. Okay. The question is, how does light go? So in this media, the speed is V2, and in this media, the speed of light is V1. Yeah. The question is, in going through this media, is there any reason for light to bend as long as the speed remains the same? It will travel along a straight line because that's the shortest path. But at the interface, when there is a transition, the main decision I want you to appreciate for a beam of light that it has to make is the following: where should it hit this interface? This is exactly analogous to the problem we had discussed a couple of lectures back, where we said if you have to compete in a triathlon where you have to swim, run and ride a bike, right? You of course have varying speeds in those different forms of locomotion. So how should you travel? Should you just travel along a straight line, or should you just try to maximize your speed or maximize the amount of time you spend in the medium where your speed is fastest? Intuitively that makes sense, no? You should travel the longer distance in that medium where you travel fast, right? But at the same time you cannot avoid this other medium. I mean, you cannot just skip. So you have to traverse a certain amount of distance, but you would like to minimize your distance of traversal in a medium where you are slowed down. That's going to be your winning strategy. So the main decision to be made here is, where should this interface be, right? So let's try and encapsulate that through a point such as this. So this is x1 and this is x2. The total distance of course is also a fixed number, it's given. This is say d. These are given. So a beam of light has to travel from the bottom of a lake to the observer's eye. The observer isn't moving, the bottom of the lake, the point in the bottom of the lake isn't changing either. So these 2 points are fixed. So x1 plus x2 is a constant. So let's write that down in the form that we are familiar with, which is a constraint, right? This is exactly in the same form as a constraint equation in 2 variables. H of x1 comma x2 is equal to 0. Yes? On the other hand, what are we actually trying to minimize here? Again, knowing the mind of light, we know what it's trying to minimize. I hope that doesn't look like a straight line, a continuous one. Yeah, I hope it looks like it's getting refracted. I don't want to give you the false impression that it's a straight line, yeah. Okay, so there is some bending, I hope that's perceptible. So what is the total length here? If this is x1 and this is d2, which is a constant number, this is under root of x1 squared plus d. Oh, okay, maybe I should rename these, just to be consistent with the 1s and 2s. So this is x2, this is x1. Yeah. So this is the length traversed in medium 2, which is x2 squared plus d2 squared under root, but that's not all. If that's the length you're traveling with a speed v2, what's the time it takes divided by v2? Yeah, so it's x2 squared plus d2 squared under root divided by v2 plus x1 squared plus d1 squared divided by v1. That's your f. Now then, Apply the same trick again. This is h. What's grad h? Very easy to see. Right? Partial with respect to x1 and x2, that's grad h. What's grad f? Very similar kind of a differentiation as before, right? So this one goes into the denominator when you differentiate with respect to x1. 2x1 gets pulled out, but 2.5 will again pulverize each other because you get 1 by 2 root x1 squared plus d1 squared. The 2.5 they take care of each other. So what you have is x1 over square root of x1 squared plus d1 squared. Of course, there's a division by v1, right? By the same token here, x2 by v2, and there's a division by the square root of x2 squared plus d2 squared. Once again, applying the same result that grad f belongs to span of grad h. That's sacrosanct for optimality, isn't it? So what then do we conclude from here? Does the familiar Snell's law pop at us from here? And if so, then how? Probably we need to define some angles here to be able to clearly see this. These are the two important angles, no? So let's call this theta 2, let's call this theta 1. So what is x1 divided by square root of x1 squared plus d1 squared in terms of theta 1? Sine theta 1, isn't it? Trigonometry. So this is sine theta 1 over v1, and this is sine theta 2 over v2, agreed? Right? Then what do we conclude from here? Because this grad f must be in the span of this, these two fellows must be equal. This is equal to some lambda times 1, 1. So this is lambda, lambda. No matter what that actual value of lambda is, the fact is that these two must be equal. Isn't that the law of refraction that we know? Right? So it's essentially a consequence of light trying to find the quickest path to get from one point to the other, the optical path. Again, something that you're familiar from studies of wave optics at some earlier stage in your career, right? But there's a particular reason why I have chosen this refraction, because this has very, very deep ramifications. We're going to introduce a very, very interesting problem, and a problem that we shall revisit several times during this course with renewed perspective. We'll try to solve this particular problem from different approaches. So suppose you have a point A at an elevation and a point B at, let's say, the ground level, right? If you want to drop an object along a guided path, how should you drop this object so that it reaches from point A to point B in the shortest amount of time? What do you think? Along an inclined plane, would that make it? Is that a good strategy? What I am saying here is this: suppose you have a point here and a point here, their altitudes are different. So there is gravity acting on a point here and on a point here as well. You want to get from this point A to this point B in the shortest amount of time. Yes? So what kind of a guided path should you create? Suppose you roll a ball along this, should you create a path like this so that the ball simply rolls along this inclined plane and you think that's the soonest that the ball can arrive from point A to point B? Or do you think that something else is warranted here? How many of you think that this is a good strategy? You have to commit to either side, whether you agree or disagree. Do you agree that this is a good starting strategy? A guess? I see a lot of you nodding yes, some of you nodding no, I don't know why, because at this point from whatever you've studied probably you haven't come across a situation where there is any other alternative that's been even suggested to you. However, if you have done some courses on aerospace engineering and if you're particularly someone fascinated by flight mechanics and stuff, you would often know that sometimes fighter jets, they do make maneuvers to get from one point to the other quickly, and what they tend to do is they tend to lose altitude. Yeah. So if you want to go from point A to point B, you can sometimes have to dip below point B and then come back to point B. That is not something that this path allows you to do. What I am talking about is some sort of a path perhaps like this. So this point C here, which is probably the lowest point of your flight, might even be lower than B. So to soar higher to a point B, you might have to dip a little lower, and you wonder why that should be so, right? Very interestingly, this is a problem that was posed by Bernoulli some 400 years back. It's a very, very celebrated problem. It's got a very interesting anecdotal sort of nuggets to it. Those are not the days of news verification, so I don't really know how much of it is true, but it is said that Bernoulli had a very clever and elegant solution to this problem. This is one of the Bernoullis, by the way, among several Bernoullis that existed, okay. And so pleased was he with his solution that he couldn't help but gloat a little and pose this as a challenge to physicists and mathematicians across Europe. And it reached a very aging Isaac Newton, okay. He took a look at it. He didn't want to appear as if he was bothered by this young upstart, yeah, so he didn't want to like take credit for solving it, but nonetheless he couldn't help but not solve it. So there he was, he solved it, he sent it out to Bernoulli, and it is said that Bernoulli, upon looking at the solution, remarked that I can identify the lion by his paws. So Newton never signed on that solution. But Newton's solution of course involved a lot of the calculus that he had developed back in the day. We'll probably get a glimpse of that kind of a solution shortly in our course. But here's why Bernoulli's solution was particularly fascinating, because the way Bernoulli approached this problem, this has got a name, it's called the Brachistochrone problem. It's a Greek name. This later part, chrone, comes from the titan of time in Greek mythology called Kronos. So it's the shortest time path, okay, the Brachistochrone problem, okay. And Bernoulli posed this problem. Bernoulli thought about it in a very clever manner. He said, I'm going to follow exactly what light does, okay, only approximate it. Because light, when it passes through different media, it sort of tends to choose the path which allows it to go fastest from one point to the other, as we've just seen. Now what if I kind of split this path up into small infinitesimal fragments and look at this as if these are small little bits of refraction happening. Now if I approximate this like a continuous curve in the limiting case by taking these splices to be infinitesimal, what sort of a curve would I get? That was his idea. So the idea starts again from the conservation of energy. How so? Well, you have a point like so, this is suppose your datum, this is y is equal to 0, okay. So at a point below here, you will have a negative value of y. So what's your total energy? It's minus mg y plus half mv squared is equal to 0. That's the conservation of energy. Yes, you start descending, you gain in speed. But that's very interesting, because now this conservation law tells us that this v is actually proportional to the square root of y. So it's not a constant speed scenario. This is gravity, right? This is the effect of the gravitational field, that your speed is not going to remain constant, much like light traveling through different media, only that now the speed is changing continuously. In case of light, you had a whole patch where your speed was held as a constant, and then in the next patch your speed was again held constant. But this is Bernoulli's clever trick. He says, I'm going to look at it in the limiting case. So in a small little splice here, I'm going to treat it as a constant speed. Yeah, at a depth of y here, it's going to be proportional. Now intuitively, you will immediately see the application of the reasoning we have just presented a while back. As you descend further and further, you gain in the speed. So you would want to live in the domain where your speed is higher and traverse a longer path, right? So you would try to quickly get from the top phase, the initial phase of your journey, and dwell longer or cover longer stretches of path along the, as you descend towards the bottom. Sometimes it may be that you will have to descend below this. So this makes sense intuitively. Yeah, this relation tells you that it makes sense. But the story doesn't end here. I mean, as in, why is this such an interesting observation? Okay, so here's why it is so interesting, because this essentially means, if you now apply the repeated law of refraction, what does it say? What did we have there? Sin theta over v was held as a constant, right? That was Snell's law for refraction. Now if v is proportional to square root of y, I might as well replace this v here with the square root of y and say that this is a constant. So that's the curve, that's the defining curve. Now if you or I look at this, we say, oh, this is still some gibberish. Gibberish as in, doesn't help my cause, does it? This is some curve which satisfies this. Why is this so interesting? But Bernoulli wasn't an ordinary man. He knew those curves and those functions and those equations like the back of his hand. One look at this and he immediately knew this is the equation of a, anyone knows? A cycloid. What is a cycloid? What is the defining feature of a cycloid? In physical terms, why is a cycloid interesting? You can think of a cycloid as this. It's like there's a circle here. The circle is rolling along this flat surface. You fixate on a particular point on this circle, yeah, and keep track of how this point travels as this circle rolls along this surface. That's the path traced out by a cycloid. Okay, I'm going to just dwell for a little while on this because it's very interesting. Otherwise, it seems very unsatisfactory that why should this be a cycloid? But I'm going to just look at the geometry of this, perhaps a zoomed version of this. So, think about a circle like so, with this being the diameter. Okay, think about this arbitrary point here. Of course, this point of contact will keep changing as the ball rotates. Momentarily, let us say this is O. Now, if you draw this particular line here, yeah, this, what can you say about this angle here? It's an angle in a semicircle and therefore it's 90 degrees. Now here's the imagination that you have to, I'll ask you to employ here. Think of this point momentarily as if this is like a pendulum. It's like a pendulum, yeah, which is fixed at this point. Of course, this point will keep changing. But if it is fixed at this point, and let's call this angle as theta. If this is theta, we know that this is also, because this is 90 degrees, right? It's a diameter. This is a tangent. So this is the diameter. So this is theta, this is 90 minus theta. This had also better be theta. Yes? Now this diameter, say little d is a constant of this circle as you traverse. What about this y here? What can we say about this? Well, first you look at this, sorry, yeah, you've already gotten to the expression, but let me just do a little bit of elementary calculation here. This is L here. So, this y upon this L, that's sine theta. Looking at this big triangle here, what else is sine theta? L upon D, isn't it? Based on this, what can you say? Yeah, what is it? D is equal to L by sine theta. Yes? What if we substitute it there? Or L is equal to D sine theta, what if we substitute this here? What do we get? Sine squared theta is equal to, is that correct? This is y. So y over L is sine theta, and here you get L over D is equal to sine theta. Yeah, so if we eliminate L, what do we get? Sine squared theta, right? Now, what do we have? If you take the square root of the positive square root, so sine theta by root y is 1 by root d, which is a constant, and therefore this, right? So indeed, once you understand this geometry here, it's quite natural to expect that this is going to be a cycloid, which is basically constantly monitoring this point as it traverses along with this rotating sphere or circle here, right? So indeed, the solution that Bernoulli came up with was very clever, but we are not just going to be satisfied with this application of static optimization. We would like to generalize this framework. Maybe this problem is solved with the ingenuity that Bernoulli displayed, but there are things that should be lurking within that should bother you a bit. Where does the source of that consternation begin? It is here. This is a function, right? Up until this point, while we were studying light, we were looking at them as straight lines, and often we just draw straight lines without even thinking. Actually, straight lines are also functions. We just take them for granted. But now this is not a straight line anymore, this is a cycloid. Yeah, and this is a function. So if you think about it for a while, what this Brachistochrone problem entails is to try and find the best possible function. Yeah, the curve given by a particular function which encapsulates the shortest time journey for a particle from point A to point B. Whatever we have learnt up till this point pertain to static optimization of within a finite dimensional setting, right? But now we are talking about functions as our possible candidates that we have to choose. Functions aren't going to be objects that necessarily live inside finite dimensional vector spaces. Take polynomials for example. Every polynomial has a finite degree. Yeah. But if you take the space of polynomials, if you say it's 20 dimensional, for instance, I'll say, well, look, a 21 degree polynomial does not live inside that vector space. So the space of functions cannot be covered within the ambit of finite dimensional vector spaces, and yet the properties are uncannily similar. You can think of functions as vectors. So we wonder what sort of ideas about vector spaces can be extended to these function spaces, and where do these similarities begin to disappear, thereby plunging us into a realm of chaos. Okay. Just to give you a quick overview of why things begin to become different when we talk about function spaces, let's look at the following situation. We'll get into the details in the next lecture. Remember, our entire definition of optimality was predicated on this notion of finding a neighborhood around the candidate point. The idea of a neighborhood had everything to do with the notion of a distance. In Euclidean spaces, the notion of distance is very natural. In function spaces, it is not so. I mean, you might be aware of several other norms in Euclidean spaces, like the 1 norm, the 2 norm, the infinity norm, or what have you, but all those norms are equivalent in the sense that they are constant scaled versions of one another. You can use any of those norms and you will still arrive at an identical notion of distance. Okay? But when you talk about function spaces, here's the catch. Look at a function like this. Okay? And then look at a function like this. Okay? If you look at them as continuous functions, where the idea of distance between functions is given like so, let us say over an interval a to b. So this is a point a comma 0, that is a point b comma 0, so that is your domain. So max over a to b. So this is the so called 0 norm. This norm you of course understand, the usual norm. So this is a 1 tuple, so it is a standard absolute value. If this was a function, I mean multi-valued like function which spits out a vector, then this would be the Euclidean norm. So this norm is defined, so you define something in terms of something that you already know. So in terms of this particular notion of closeness or distance, it would seem like these fellows are not very far off, because what you are going to do is you are going to call one of them f1, the other as f2, and you are going to look at f1 minus f2, the 0 norm thereof. Yeah, and you are going to say, oh okay, not too bad, they are pretty close. So maybe one is a close approximation of the other, if you are only considering continuous functions. Now suppose you consider not just continuous functions but also continuously differentiable functions. Immediately this fellow I have drawn in orange will cease to be a candidate, right? There are so many points here at which it is not differentiable. Yes? So therefore this candidate no longer even enters within that realm. In fact, you can also define the 1 norm in this following manner. Yeah, that is a 0 normal function, that is a 1 normal function. You immediately see that in some cases one of those does not even exist. Forget about those norms conveying the same notion. Even if they did exist and you have a low frequency sinusoid here of small amplitude and a high frequency sinusoid here of equally small magnitude, both being differentiable, do you think that the derivatives will come close by? Even if these terms do not throw up something very large in the difference, if I replace this with 1 here, this term might be pretty large, no? Because the omega might be large in one and the omega might be small in the other. When you differentiate, it gets multiplied by omega. So in their derivatives, they might be far apart. So when you are factoring in things like derivatives and higher derivatives, things might be vastly different. So just to be clear, when you are going into smoother functions, you can always use the coarser sort of norm such as this. So, if you have continuously differentiable function, you can use both of these norms. If you have only continuous function, you cannot use this very naturally, right. If you have twice continuously differentiable function, you can use both of these as well as another where you append to this naturally the second derivative with respect to x. But for continuously differentiable, that does not appear as a candidate norm. So, you can keep defining these different ideas of norms. The 0 and 1 norm are the things that we shall be mostly interested in this particular course. When we come back in the next lecture, we shall see that these give rise very naturally to the idea of a stronger extrema and a weaker extrema, and we will also have some discussions to be had on that matter. Okay, so that is all for